Tonight, we are going to explore one of the most provocative and mind-bending ideas in modern cosmology, a theory that sounds like pure science fiction, but is rooted in serious mathematical physics and supported by observations from the most powerful telescope humanity has ever built. The claim is audacious, almost absurd in its implications. Scientists suggest that our entire universe, everything we can see and everything we cannot, all the galaxies and stars and planets and empty space stretching out for billions of light years in every direction, might exist inside a black hole. Not metaphorically, not as an analogy, but literally, physically, as the interior region of a black hole that itself exists within a larger parent universe. And recent observations from the James Webb Space Telescope have provided what some researchers are calling overwhelming evidence that this radical idea might actually be true. Before we continue, if you enjoy these deep explorations into the cutting edge of cosmology and physics, a quick like or subscribe would mean a great deal. It helps the channel grow and allows me to continue creating content that tackles the biggest questions in science. Now, let us dive into this extraordinary claim and carefully examine what scientists have actually discovered, what the theory really says, and whether we should take it seriously. The idea that we might be living inside a black hole is not new. It has been proposed in various forms over the decades by a small group of theoretical physicists willing to think outside the conventional boundaries of cosmology. But it remained largely speculative, an interesting mathematical possibility without clear observational support until recently. In 2025, a study analyzing galaxies observed by the James Webb Space Telescope revealed something completely unexpected, something that the standard model of cosmology cannot easily explain. When researchers examined the rotation directions of 263 galaxies in the deep universe, galaxies so distant that we are seeing them as they appeared billions of years ago when the universe was young, they found that these galaxies do not rotate randomly. About 2/3 of them rotate in one direction, what we perceive as clockwise from our vantage point, while only about 1/3 rotate in the opposite direction, counterclockwise. This might not sound particularly shocking until you understand what cosmologists have always assumed about the universe. The standard cosmological principle, one of the foundational assumptions underlying modern cosmology, states that the universe should be isotropic and homogeneous on large scales. Isotropic means it looks the same in all directions. Homogeneous means it has the same properties everywhere. If this principle is correct, then galaxies should show no preferred direction of rotation. We should see roughly equal numbers rotating clockwise and counterclockwise, a 50-50 split, because there is no reason for the universe to favor one direction over another. The universe should have no preferred axis, no cosmic up or down, no special direction. Yet the James Webb observations show a clear asymmetry, a statistically significant preference for one rotational direction over the other. This is not a small effect that can be dismissed as measurement error or random chance. The difference is so obvious that, according to the researcher who published the study, anyone looking at the images can see it without needing special knowledge or analysis tools. So what could explain this unexpected asymmetry? There are essentially two possibilities, and both are profound in their implications. The first is that we have been measuring distances in the universe incorrectly, that observational biases related to the Milky Way's own rotation have skewed our observations in ways we did not fully account for. If this is true, it means we need to recalibrate our cosmic distance measurements, which could resolve several other puzzling observations in cosmology, including why some galaxies appear older than the universe itself, and why different methods of measuring the universe's expansion rate give slightly different answers. The second possibility is more radical. It suggests that the universe itself was born rotating, that it has an intrinsic preferred axis, a cosmic spin inherited from something that existed before the Big Bang. And one of the few theories that naturally predicts such a preferred axis is the hypothesis that our universe is the interior of a black hole formed in a larger parent universe. To understand how we could possibly be living inside a black hole, we first need to understand what black holes actually are and how they relate to the structure of spacetime. A black hole is a region of spacetime where gravity is so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity, compressing the star's core into an incredibly dense point. According to Einstein's general theory of relativity, which describes gravity as the curvature of spacetime caused by mass and energy, the collapse of a massive star's core creates a gravitational well so deep that spacetime curves back on itself. The event horizon marks the point of no return, the boundary where the escape velocity equals the speed of light. Anything that crosses the event horizon, whether matter, energy, or information, falls inexorably toward the center. Inside the event horizon, according to classical general relativity, the collapsing matter continues to compress until it forms a singularity, a point of infinite density where the laws of physics as we understand them break down completely. Singularities are problematic for physicists because infinity is not a physical value. It suggests that our theories are incomplete, that general relativity cannot describe what actually happens at the center of a black hole. For decades, physicists have sought ways to avoid singularities, to find modifications of general relativity that prevent matter from compressing to infinite density. One such modification is called Einstein-Cotton theory, an extension of general relativity that takes into account a property of matter called intrinsic spin. In standard general relativity, spacetime has curvature but not torsion. Curvature describes how spacetime bends in response to mass and energy, like a bowling ball creating a dip in a stretched rubber sheet. Torsion, on the other hand, describes a twisting of spacetime, a rotation or spiraling of the geometric fabric itself. Einstein-Cotton theory, proposed in the early 20th century but largely overlooked until recently, adds torsion to the mathematics of general relativity. In this modified theory, particles with spin, which includes all fundamental matter particles like electrons, protons, and neutrons, create not just curvature but also torsion in spacetime. Under normal conditions, torsion is negligibly small and has no observable effects. But at the extreme densities found inside black holes or in the very early universe, torsion becomes significant and produces a repulsive force that counteracts gravitational compression. This is where the work of theoretical physicist Nikodem Poplawski becomes crucial to our story. Poplawski, currently a distinguished lecturer in physics at the University of New Haven, has spent years developing the mathematical details of what happens when you apply Einstein-Cotton theory to black holes and cosmology. His key insight is that torsion prevents the formation of singularities. When matter collapses inside a black hole, torsion generates a repulsive force that becomes stronger as the density increases. This force eventually halts the collapse at an enormous but finite density, preventing the matter from compressing to a mathematical point. Instead of forming a singularity, the collapsing matter undergoes what Poplawski calls a big bounce. The matter reaches maximum compression, stops, and then rebounds, expanding outward again. But here is the crucial point. This rebound does not happen in the same spacetime region where the black hole exists as seen from outside observers. Instead, it happens on the other side of the event horizon, in a new region of spacetime that is causally disconnected from the parent universe. From the perspective of observers in the parent universe, the black hole forms normally. A massive star collapses, an event horizon appears, and the black hole settles into a stable configuration characterized by its mass, spin, and electric charge. Time appears to slow down near the event horizon due to gravitational time dilation, and from the external viewpoint, anything falling into the black hole takes an infinite amount of time to actually cross the horizon. But from the perspective of matter falling through the event horizon, something completely different happens. It crosses the horizon in finite time, experiences the torsion-driven bounce, and finds itself in a new expanding universe. The event horizon acts as a one-way membrane separating two regions of spacetime. The parent universe and the new baby universe cannot communicate or interact after the black hole forms. The baby universe expands and evolves according to its own physics, completely isolated from the parent universe that gave birth to it. This scenario has profound implications for understanding our own universe. If Poplawski's theory is correct, then every black hole in our universe could contain an entire universe on its other side, a cosmos with its own galaxies, stars, and possibly even life, all existing in a spacetime region completely cut off from ours. And more provocatively, our own universe could have originated not from a singular Big Bang, but from a big bounce inside a black hole that formed in some parent universe. The Big Bang in this picture is not the beginning of all existence, but rather a phase transition, a rebound from maximum compression, occurring inside a black hole event horizon. The rapid expansion we observe, the fact that the universe started small and has been growing ever since, is explained as the natural consequence of this bounce and the subsequent expansion of the new spacetime region. One of the attractive features of this black hole universe hypothesis is that it potentially solves several long-standing problems in cosmology. The standard Big Bang model, while tremendously successful at explaining many observations, has some uncomfortable features. It requires that the universe began from a singularity, a physically impossible state of infinite density. It struggles to explain why the universe is so uniform on large scales when regions that appear causally connected, that appear to have influenced each other, were actually too far apart in the early universe to have ever communicated. This is called the horizon problem. The standard solution is cosmic inflation, a period of exponentially rapid expansion in the first fraction of a second after the Big Bang that stretched the universe by many orders of magnitude. Inflation solves the horizon problem and explains why the universe appears spatially flat rather than curved. But inflation itself requires explanation. It requires adding new physics, a hypothetical inflation field that somehow turned on, drove the exponential expansion, and then turned off again. Inflation works mathematically but feels somewhat arbitrary, like adding an epicycle to save a theory. In Poplawski's black hole cosmology, the rapid early expansion of the universe is not driven by an ad hoc inflation field, but is instead a natural consequence of the Big Bounce and the torsion-driven repulsion that occurs at extreme densities. The universe bounces and then expands rapidly because the torsion force is pushing it apart. As the density decreases and the universe grows, torsion becomes less important and the expansion settles into the more gradual growth we observe today, driven by the remaining energy density and the mysterious dark energy that appears to be accelerating the expansion. This scenario, according to Poplawski, produces inflation-like expansion without needing to invoke a special inflation field. It is a more economical explanation, relying only on a well-defined modification of general relativity rather than adding entirely new physics. Another advantage of the black hole universe idea is that it avoids singularities entirely. There is no moment of infinite density at the beginning of our universe, just a moment of very high but finite density during the bounce. And there are no singularities inside the black holes in our universe either, because torsion prevents them from forming. This removes one of the most conceptually troubling aspects of general relativity, the prediction that singularities exist, and that at these points the theory itself breaks down. If Einstein-Cartan theory is the correct description of gravity, then singularities never actually form, and spacetime remains well-behaved even under the most extreme conditions. Now we come to the recent observational evidence that has brought this theory back into the spotlight. If our universe was born inside a black hole, then it should have inherited certain properties from that parent black hole. Black holes, according to observations and theory, almost always rotate. Stars rotate, and when a star collapses to form a black hole, conservation of angular momentum means the black hole must rotate as well, often very rapidly. If our universe formed inside a rotating black hole, then the axis of rotation of that parent black hole would manifest itself as a preferred direction in our universe, a cosmic axis that influences large-scale structure. This is exactly what the James Webb observations might be revealing. The study, published in 2025 by Lior Shamir of Kansas State University in the monthly notices of the Royal Astronomical Society, analyzed galaxies from the JWST Advanced Deep Extragalactic Survey, focusing on galaxies clear enough to determine their rotational direction. The result was striking. Of 263 galaxies analyzed, approximately 175 rotated in one direction, while only 88 rotated in the opposite direction, a roughly 2-to-1 ratio that deviates significantly from the expected 50-50 split. This asymmetry was found specifically in galaxies at high redshift, meaning we are observing them as they were in the early universe, billions of years ago. Previous observations using ground-based telescopes had hinted at similar asymmetries, but with smaller sample sizes and less dramatic differences. The James Webb data, with its unprecedented clarity and depth, confirmed and strengthened these earlier suggestions. When Poplawski learned of these findings, he told reporters that this would be fascinating if confirmed, saying that a preferred axis in our universe could be naturally explained by the theory that our universe was born on the other side of an event horizon of a black hole existing in some parent universe. He emphasized that most black holes rotate because they form from rotating stars or at the centers of rotating galaxies, and this rotation would influence the universe created inside the black hole. In his words, the simplest explanation of a rotating universe is that the universe was born in a rotating black hole. The mechanism by which the parent black hole's rotation would influence the baby universe is subtle but important. When a rotating black hole forms, its rotation creates frame-dragging effects in the surrounding spacetime, literally twisting the fabric of space so that anything nearby is dragged along with the rotation. Inside the event horizon, this frame dragging becomes extreme. The spacetime itself is rotating, and this rotation would be imprinted on the new universe that forms through the Big Bounce. The axis of rotation would create a preferred direction, and matter and energy in the new universe would be influenced by this direction. Over billions of years, as galaxies form and evolve, this subtle preference could manifest as an observable asymmetry in galaxy rotation directions. The galaxies would not all rotate the same way, but there would be a statistical bias, exactly what the James Webb observations appear to show. It is important to understand what this evidence does and does not prove. The observation that galaxies show a preferred rotation direction is real and published in a peer-reviewed journal. It is not a misunderstanding or a fabrication. However, there are alternative explanations that do not involve black hole cosmology. The most prosaic explanation is that observational biases are skewing the results. The Milky Way galaxy, our home, is itself rotating, and this rotation gives Earth a velocity relative to the distant galaxies we observe. Due to the Doppler effect, galaxies moving toward us appear slightly brighter than galaxies moving away. If galaxies rotating in a certain direction relative to the Milky Way tend to have more of their light Doppler shifted toward us, they might appear overrepresented in telescope surveys. This could explain the asymmetry, without requiring any fundamental change to cosmology. Shamir, the researcher who published the study, acknowledges this possibility and notes that if the Milky Way's rotation is influencing observations more than previously thought, then astronomers may need to recalibrate their distance measurements for the deep universe. Such a recalibration could potentially resolve other puzzling observations in cosmology, including the tension between different measurements of the Hubble constant, the rate at which the universe is expanding. and the problem of galaxies that appear to be older than the universe itself based on current distance estimates. So even if the black hole universe explanation is wrong, the James Webb findings are pointing towards something important that cosmologists need to address. But let us suppose for a moment that the black hole cosmology interpretation is correct and explore what it would mean. If our universe is indeed the interior of a black hole in a larger parent universe, then several testable predictions follow. First, our universe should be closed rather than flat or open. In cosmological terms, a closed universe is one with positive spatial curvature, like the surface of a sphere. If you traveled far enough in a straight line through a closed universe, you would eventually return to your starting point, just as traveling east on Earth eventually brings you around to where you began. Observations so far suggest that our universe is very close to spatially flat, meaning parallel lines remain parallel, and the geometry is Euclidean. However, measurements are not precise enough to rule out a very slight positive curvature. If future observations, perhaps from improved measurements of the cosmic microwave background, or from mapping the large-scale distribution of galaxies with greater precision, reveal that the universe is indeed closed, this would support the black hole universe hypothesis. Second, if the universe formed from a rotating black hole and inherited a preferred axis, then we should see evidence of this axis not only in galaxy rotation directions, but potentially in other large-scale structures, and in the cosmic microwave background radiation itself. The cosmic microwave background, the afterglow of the Big Bang visible as faint microwave radiation coming from all directions in the sky, is remarkably uniform, but contains tiny temperature fluctuations at the level of 1 part in 100,000. These fluctuations represent the seeds from which galaxies and galaxy clusters eventually formed. If the universe has a preferred axis, there might be subtle patterns in these fluctuations aligned with that axis. Some researchers have claimed to see hints of such patterns, sometimes called the axis of evil in cosmology, because it violates the expected statistical isotropy. But these claims remain controversial and are debated in the scientific community. Third, the black hole universe model makes predictions about the nature of dark energy, the mysterious force that appears to be accelerating the expansion of the universe. In standard cosmology, dark energy is often modeled as a cosmological constant, an intrinsic property of empty space that creates a repulsive gravitational effect. But its origin and nature remain deeply mysterious. In some formulations of black hole cosmology, the apparent dark energy could be related to the geometry of spacetime inside the black hole, or to residual effects of the torsion that drove the initial bounce and expansion. If this is correct, then careful measurements of how dark energy behaves over cosmic time might reveal subtle differences from the simple cosmological constant model. However, and this is crucial, none of these predictions have been confirmed yet, and several face significant challenges. The idea that our universe exists inside a black hole is not mainstream cosmology. It is a speculative hypothesis proposed by a small group of researchers and viewed with skepticism by most cosmologists. The standard Big Bang model with cosmic inflation, despite its conceptual oddities, has been extraordinarily successful at explaining a wide range of observations. It predicts the abundances of light elements like hydrogen and helium formed in the first few minutes after the Big Bang, and these predictions match observations beautifully. It predicts the existence and detailed properties of the cosmic microwave background, and again the observations confirm the predictions with remarkable precision. It predicts the large-scale structure of the universe, how galaxies are distributed in clusters and superclusters, and this too matches what we observe. Any alternative theory must explain all of these same observations, at least as well as the standard model does. Poplawski's Einstein-Cartan black hole cosmology does offer explanations for many of these observations, and it has the advantage of avoiding singularities and potentially explaining inflation without adding new physics. but it also makes the universe more complicated in other ways. It requires that Einstein-Cartan theory, rather than standard general relativity, is the correct description of gravity. While Einstein-Cartan theory is mathematically consistent and adds torsion in a natural way by accounting for the spin of particles, we have no direct observational evidence that torsion exists in nature. All tests of general relativity so far are consistent with the standard version without torsion. Torsion effects would only become noticeable at extremely high densities that we cannot replicate in laboratories or observe directly. So we are extrapolating from well-tested physics at normal densities to completely untested physics at extreme densities, and that extrapolation might be wrong. Moreover, even if Einstein-Cartan theory is correct and black holes create new universes through big bounces, this does not necessarily mean our universe formed this way. It is logically possible that our universe began with a standard Big Bang singularity while other universes form inside black holes. The theory allows for both possibilities. The question is which one describes our actual universe, and that requires observational evidence, which brings us back to the James Webb findings and other potential observations. The galaxy rotation asymmetry is intriguing but not conclusive. It could be explained by observational biases, and even if it is real and cosmic in origin, there might be other explanations besides black hole cosmology. For example, some speculative theories involving quantum effects in the very early universe or connections to string theory might also predict a preferred cosmic axis. More observations are needed to test these alternatives against each other. Another challenge for black hole cosmology is that it does not truly solve the problem of origins. It simply pushes the question back one level. If our universe formed inside a black hole in a parent universe, then where did the parent universe come from? Poplawski and others who work on this theory acknowledge this openly. The most natural answer within the framework of black hole cosmology is that the parent universe itself formed inside a black hole in a grandparent universe, which formed inside a black hole in a great-grandparent universe, and so on, an infinite chain of universes nested inside black holes all the way back. This is sometimes called eternal inflation in the context of standard cosmology, but here it is eternal black hole formation. It avoids the need for an absolute beginning, a moment of creation from nothing, but it replaces that with an infinite regress, which some find equally troubling philosophically. There is no first universe, no ultimate origin point, just universes giving birth to universes forever into the past. From a scientific standpoint, an infinite regress is not necessarily a problem as long as the theory makes testable predictions about our own universe. Science does not require that we explain everything, only that we explain the phenomena we can observe. If black hole cosmology makes testable predictions that distinguish it from competing theories, and if observations confirm those predictions, then it succeeds as a scientific theory regardless of whether it answers ultimate questions about origins. But we are not there yet. The theory remains speculative, supported by suggestive observations but not definitively confirmed. It is also worth noting that the recent media coverage of the James Webb Galaxy rotation findings, while based on real published research, has sometimes overstated the strength of the evidence and the level of scientific consensus. Headlines declaring that scientists have proved we live inside a black hole are misleading. No such proof exists. What exists is an interesting observation that is consistent with black hole cosmology, but that also has alternative explanations. Poplawski himself, when commenting on the findings, used careful language, saying the results would be fascinating if confirmed and that they could support the theory. He did not claim they prove the theory. This distinction is important. In science, even strong evidence rarely proves a theory absolutely. Instead, evidence accumulates over time, and competing theories are gradually ruled out or shown to be less likely, until one explanation emerges as the best available given current knowledge. The nature of scientific progress is that bold new ideas often begin on the fringes, proposed by small groups of researchers willing to challenge conventional wisdom. Sometimes these ideas turn out to be correct, and they eventually become the new mainstream. The Big Bang itself was once a fringe idea, ridiculed by many astronomers who preferred the steady-state model of an eternal, unchanging universe. Plate tectonics, the idea that continents drift across the Earth's surface, was rejected for decades before finally being accepted in the 1960s. Black holes themselves were considered purely theoretical curiosities until observational evidence became overwhelming. So we should not dismiss black hole cosmology simply because it is currently a minority view, but neither should we accept it uncritically just because it is interesting or because some observations seem to support it. The proper scientific attitude is to remain open-minded but skeptical, to examine the evidence carefully, and to insist on rigorous testing of predictions. What would it take to confirm or refute black hole cosmology conclusively? Several different types of observations could provide stronger evidence one way or the other. First, more detailed measurements of the cosmic microwave background could reveal whether there is truly a preferred axis in the universe. Current missions like the Planck satellite have produced extraordinarily detailed maps of the microwave background, but future missions with even greater sensitivity and resolution might detect subtle patterns that are currently below the noise threshold. If a clear preferred axis is found, and if it aligns with the axis suggested by the galaxy rotation asymmetry, that would strengthen the case for a rotating universe. If no such axis is found despite improved observations, it would argue against black hole cosmology. Second, more precise measurements of the curvature of space could determine whether the universe is truly flat or whether it has a slight positive curvature consistent with being closed. Several independent methods can measure curvature, including analyzing the geometry of the cosmic microwave background fluctuations, measuring how galaxies cluster on very large scales, and studying the paths of light rays from distant objects. If these methods converge on a consistent answer showing positive curvature, it would support the prediction that the universe is closed as expected if it is inside a black hole. If they confirm that the universe is exactly flat or even has negative curvature, it would be difficult to reconcile with black hole cosmology. Third, the galaxy rotation asymmetry itself needs to be confirmed with larger samples and different methods. The James Webb finding was based on 263 galaxies, a substantial number but not enormous by the standards of modern astronomy. Surveys of thousands or tens of thousands of galaxies across different regions of the sky and at different distances could confirm whether the asymmetry is real and universal, or whether it was a statistical fluke or localized to the particular region observed. Different researchers using different classification methods should analyze the data independently to check for systematic biases. If the asymmetry persists and strengthens with more data, it becomes harder to dismiss. If it disappears or reverses in other samples, it suggests the original finding was not cosmologically significant. Fourth, direct searches for torsion effects could provide evidence for or against Einstein-Cartan theory. While torsion should be negligible under normal conditions, there are proposals to look for extremely subtle effects in precision experiments or in observations of very dense environments like neutron stars. If torsion is detected, it would validate the theoretical foundation underlying Poplawski's cosmological model. If extensive searches find no evidence for torsion, it would suggest that standard general relativity without torsion is correct, undermining the physical basis for the black hole bounce mechanism. The philosophical implications of living inside a black hole are worth considering even if the theory remains unproven. If black hole cosmology is correct, it fundamentally changes our understanding of the universe's place in a larger cosmic structure. We are not living in the one and only universe that began with the Big Bang and will end with heat death or collapse. Instead, we are living in one universe among potentially countless others, each one formed inside a black hole, and each one completely isolated from the others by event horizons. This is a form of multiverse, but not the quantum many-worlds multiverse or the string theory landscape multiverse that physicists often discuss. It is a multiverse of causally disconnected spacetime regions, each with its own history and its own laws determined by the conditions under which its parent black hole formed. In this picture, every black hole in our universe might contain an entire cosmos, a universe with its own galaxies, stars, planets, and perhaps even intelligent beings pondering the nature of their reality. The black holes we observe through telescopes, from stellar mass black holes formed in supernova explosions to the supermassive black holes at the centers of galaxies, could each be the birthplace of a universe. And those universes might contain their own black holes which spawn their own universes, creating an endless fractal structure of universes within universes, each generation isolated from the previous one by the one-way membrane of the event horizon. This is a cosmos far vaster and stranger than the already incomprehensibly large observable universe we can see with our telescopes. Also raises intriguing questions about the nature of time and causality. If our universe is inside a black hole in a parent universe, then from the perspective of observers in that parent universe, the formation of our universe happened at a specific moment when the black hole's event horizon formed. But from our perspective inside, time flows normally, and the universe has existed for 13.8 billion years. These two time scales are related by extreme gravitational time dilation. What appears to us as billions of years of cosmic evolution might correspond to only a brief moment in the parent universe's time, or conversely, an enormous span of time in the parent universe might elapse while only an instant passes for us. The relationship depends on the details of the black hole's properties and the geometry of spacetime near the event horizon. There is also the question of whether information can ever escape from a black hole universe back into the parent universe. In standard black hole physics, there is a famous information paradox. Quantum mechanics says that information cannot be destroyed, but general relativity says that anything falling into a black hole is lost forever behind the event horizon and eventually crushed at the singularity. This apparent contradiction has troubled physicists for decades. Stephen Hawking proposed that black holes gradually evaporate through quantum effects, emitting what is now called Hawking radiation, and that in principle the information might be encoded in this radiation in a highly scrambled form. But the details remain controversial. In black hole cosmology, the information does not need to return to the parent universe. It exists in the baby universe, preserved in the matter and energy that rebounded from the Big Bounce. From this perspective, information is not destroyed when matter falls into a black hole. It is simply transferred to a new spacetime region where it continues to exist and evolve. Now let us step back and assess where we are in this discussion. We started with a dramatic claim that scientists have proved we are living inside a black hole, and we have examined the evidence and the theory behind this claim. What can we conclude? First, no such proof exists in the strict scientific sense. The James Webb observations of asymmetric galaxy rotation are real and published, but they do not conclusively prove black hole cosmology. They are consistent with that theory, but they are also potentially explainable through observational biases or other mechanisms. The black hole universe hypothesis remains speculative, an interesting idea with some supporting evidence but not a confirmed fact. Second, the theory itself, based on Einstein-Cartan gravity with torsion, is mathematically consistent and solves some conceptual problems with standard cosmology, particularly the singularity problem and potentially the need for an ad hoc inflation field. However, it also introduces new complexity and relies on physics that has not been directly tested. Most cosmologists working in the field do not currently accept black hole cosmology as the best explanation for the universe's origin and large-scale structure. The standard Big Bang model with inflation remains the dominant paradigm because it successfully explains a wide range of observations. Third, the recent observations from the James Webb Space Telescope have reignited interest in this theory and provided what some researchers view as the first potentially significant observational support. Whether this evidence holds up under further scrutiny remains to be seen. More observations, more careful analysis, and independent confirmation are needed before the scientific community will seriously consider adopting black hole cosmology as a mainstream theory. This is how science should work. Bold ideas are proposed, evidence is gathered, debates occur, and gradually a consensus emerges based on which theory best explains the totality of available data. It is also important to recognize that the question of whether we live inside a black hole is not just an abstract academic debate. The answer has profound implications for our understanding of the cosmos and our place within it. If black hole cosmology is correct, it means that the universe is far more vast and complex than we imagined, with layers of reality stacked inside black holes in an infinite regression. It means that the Big Bang was not the absolute beginning of everything, but rather a phase transition within a larger eternal structure. It means that creating a black hole, which happens naturally when massive stars collapse, is not just an end but also a beginning, the birth of a new universe complete with its own spacetime, its own physical laws, and its own potential for complexity and life. If black hole cosmology is wrong and the standard model is correct, then the Big Bang was indeed the origin of all space, time, matter, and energy, at least in our universe. The questions of what came before, if anything, and what caused the Big Bang, if causation even makes sense in that context, remain fundamentally mysterious. Perhaps future theories of quantum gravity, if we ever develop a successful one, will provide answers. Perhaps they will show that the very notion of a beginning is ill-defined or meaningless. Or perhaps there are limits to what physics can explain, ultimate questions that lie beyond the reach of scientific investigation. These are deep philosophical waters, and cosmology in the 21st century is forcing us to confront them. The black hole universe hypothesis also highlights how much we still do not understand about fundamental physics. Despite the tremendous success of general relativity and quantum mechanics, we know these theories are incomplete. They cannot both be correct as currently formulated because they give contradictory predictions in extreme conditions like the center of black holes or the moment of the Big Bang. We need a theory of quantum gravity that unifies these two pillars of modern physics, but despite decades of effort, no such theory has been confirmed. String theory, loop quantum gravity, and other approaches offer possibilities, but none has made testable predictions that have been verified by observation. Einstein-Cartan theory is another approach, one that modifies general relativity to include torsion and thereby avoid singularities. It is one among several competing ideas, and only observations can tell us which, if any, is correct. As we look to the future, the prospects for testing black hole cosmology are better than they have ever been. The James Webb Space Telescope is still in its early years of operation and will continue to provide unprecedented views of the distant universe. Other missions are planned that will measure the cosmic microwave background with even greater precision. Ground-based telescopes with mirrors tens of meters across are under construction, capable of detecting and analyzing thousands of distant galaxies. Gravitational wave observatories are becoming more sensitive and will eventually detect mergers of black holes and neutron stars throughout the universe, potentially revealing new physics in extreme gravitational fields. All of these observations will provide data that can test cosmological models, including black hole cosmology. What remains consistent throughout is the importance of maintaining scientific rigor and intellectual honesty. It is exciting to contemplate the possibility that our entire universe exists inside a black hole. It captures the imagination and suggests a cosmos far stranger and more wonderful than everyday experience would suggest. But excitement is not evidence. We must follow the data wherever it leads, even if it leads to more mundane conclusions. Science advances through the confrontation of ideas with reality, and reality, as revealed through careful observation and experiment, always has the final word. The universe does not care what we want to be true or what would make a better story. It simply is what it is, and our job as scientists and as curious individuals is to discover what that is through patient investigation and critical thinking. If you have stayed with me through this extended exploration of black hole cosmology, I hope you have gained not only an understanding of this specific theory, but also an appreciation for how science grapples with profound questions about the nature of reality. We have examined a bold claim, looked at the evidence supporting it and the evidence against it, considered alternative explanations, and assessed the current state of scientific knowledge. This is the process by which humanity gradually comes to understand the universe. It is not always neat or straightforward. There are false starts, controversies, and sometimes decades or centuries pass before definitive answers emerge. But the process works. Our understanding of the cosmos has grown immeasurably over the past few centuries, from thinking Earth was the center of everything to recognizing that we inhabit one planet among billions in one galaxy among trillions, from believing the universe was eternal and unchanging to discovering that it had a beginning and has been expanding for nearly 14 billion years. From viewing black holes as purely theoretical curiosities to observing them directly and using them as tools to test fundamental physics. The question of whether we live inside a black hole represents the frontier of this ongoing quest for understanding. It might turn out to be true, in which case future generations will look back and recognize the James Webb Galaxy rotation observations and other emerging evidence as the first hints of a profound shift in our cosmological paradigm. Or it might turn out to be wrong, a creative idea that sparked useful research but ultimately was not supported by the totality of evidence. Either outcome contributes to the progress of science. Even if black hole cosmology is refuted, the attempt to test it will have refined our observational techniques, sharpened our theoretical understanding, and perhaps revealed unexpected phenomena that point toward different answers. What we can say with confidence is that cosmology today is in an exciting state. We have powerful new observational tools like the James Webb Space Telescope. We have sophisticated theoretical frameworks like Einstein-Cartan theory and various approaches to quantum gravity. And we have concrete observations that challenge our assumptions and demand explanation. The asymmetric galaxy rotation is real. Whatever causes it, whether observational bias, cosmic rotation from a parent black hole, or some entirely different mechanism, requires a scientific explanation. The process of developing and testing these explanations, of arguing about which best fits the data, of devising new observations to distinguish between alternatives, this is science at its most vibrant and productive. For those of us watching from the sidelines, following the developments through news reports and scientific publications and videos like this one, it is a privilege to witness this process unfold. We are living through a period when fundamental questions about the nature of the universe are being actively investigated with better tools than ever before. Within our lifetimes, we may learn answers to questions that have puzzled humanity for millennia. We may discover that the universe is even stranger than we currently imagine, or we may find that the standard models we have developed are remarkably accurate and complete. Either way, the journey of discovery continues, and we are fortunate to be alive at a time when we can follow along and appreciate the grandeur of what is being revealed. Before we conclude, I want to address a broader point about scientific communication and how news about discoveries like the James Webb Galaxy rotation findings gets presented to the public. There is often a tension between accuracy and engagement, between careful, nuanced presentation and attention-grabbing headlines. A headline saying scientists discover galaxies rotate asymmetrically, possibly due to observational biases or cosmic rotation, is accurate but not very compelling. A headline saying, "Scientists just proved we're living inside a black hole," is compelling but not accurate. The truth, as so often happens, lies somewhere in between. Scientists have discovered an interesting and potentially significant observation. This observation is consistent with a speculative theory that suggests we might live inside a black hole. But the observation does not prove that theory, and alternative explanations exist. Conveying this accurately while still capturing the genuine excitement and importance of the discovery is challenging. My goal in this video has been to present the full picture, to explain the theory in enough detail that you understand what it actually claims, to describe the observations that have sparked renewed interest, to discuss the evidence both for and against, and to place everything in the context of how science actually works. Headlines and brief news articles often cannot do justice to this complexity, which is why longer-form content like this, where we can take the time to really dig into a topic, serves an important role in scientific communication. If you found this approach valuable, I hope you will like this video and subscribe to the channel so that I can continue creating content that explores these fascinating questions in depth. The cosmos is vast and strange and beautiful. It operates according to laws that we are still discovering, laws that sometimes match our intuitions and sometimes violate them completely. The possibility that we might be living inside a black hole, that our entire universe with all its galaxies and stars and planets might be just one of countless universes nested inside black holes in an infinite fractal structure, is one of the more mind-bending ideas that serious scientists have proposed. It may be true, or it may be false, but either way it represents human imagination and mathematical skill being applied to the deepest questions we can ask. What is the universe? Where did it come from? What is its structure and its fate? These questions have driven astronomy and physics for centuries, and they continue to drive research today. As we have seen throughout this exploration, answering these questions requires a combination of theoretical insight, mathematical sophistication, technological innovation, and careful observation. It requires building telescopes powerful enough to see galaxies billions of light years away and sensitive enough to measure tiny asymmetries in their properties. It requires developing theories like Einstein-Cartan gravity that extend our understanding of spacetime and matter. It requires analyzing data carefully, accounting for biases and systematic errors, and honestly assessing what the data does and does not tell us. And it requires patience, the recognition that some questions cannot be answered quickly, that some mysteries take decades or generations to solve, and that this is simply the nature of doing science at the frontiers of human knowledge. The universe revealed by modern cosmology is almost incomprehensibly large. The observable universe extends for 93 billion light-years across, containing an estimated 2 trillion galaxies, each with hundreds of billions of stars, many of those stars with their own planetary systems. The total number of planets in the observable universe likely numbers in the sextillions. This is the universe we can see, the region from which light has had time to reach us since the Big Bang. Beyond this observable horizon lies more universe, potentially infinite in extent, that we can never observe because the light from those regions has not yet had time to reach us, and due to cosmic expansion, never will. This alone is staggering to contemplate. But if black hole cosmology is correct, this incomprehensibly vast observable universe is itself contained within a black hole that exists in a larger parent universe, which might be similarly vast or even larger, and that parent universe might itself be inside a black hole, and so on without end. The scale of reality, if this is true, becomes not just vast but literally infinite, with infinitely many universes stacked inside each other, each one a complete cosmos in its own right. Even if black hole cosmology is wrong, the implications of what we do know about the universe are profound. We know that space is expanding, carrying galaxies away from each other at speeds that increase with distance. We know that the early universe was much hotter and denser than it is today, and that it has been cooling and expanding for 13.8 billion years. We know that the matter we are made of, the ordinary atomic matter of stars and planets and people, constitutes only about 5% of the total energy content of the universe. The rest is dark matter, whose nature we do not understand but whose gravitational effects we observe, and dark energy, a mysterious force driving the acceleration of cosmic expansion. We know that black holes exist, that spacetime can be curved and warped by gravity, and that the universe began in a state of extremely high density and temperature from which all current structure evolved. These are not speculations. They are established facts supported by overwhelming observational evidence. They paint a picture of a universe that is dynamic, evolving, and fundamentally different from the static eternal cosmos that ancient philosophers imagined. The search for deeper understanding continues. Questions about the nature of dark matter and dark energy, about the ultimate fate of the universe, about what if anything came before the Big Bang, about whether our universe is unique or one among many in a multiverse, about whether the fundamental constants of nature could have been different or are somehow necessary. All of these remain open. Black hole cosmology addresses some of these questions, offering answers that are intriguing if unproven. But regardless of whether this particular theory is correct, the questions themselves are worth asking, and the attempts to answer them push the boundaries of human knowledge and capability. Every telescope we build, every theoretical framework we develop, every observation we make adds another piece to the puzzle. Sometimes the pieces fit together easily, confirming what we already suspected. Sometimes they do not fit at all, forcing us to rethink our assumptions and develop new ideas. This process of ongoing discovery and revision is the heart of science, and it is what makes cosmology such a vibrant and exciting field. We are fortunate to live in an era when we can not only ask these profound questions, but also hope to answer some of them through observation and experiment. Ancient philosophers could speculate about the nature of the cosmos, but had no way to test their speculations. Medieval scholars had limited tools and could only observe the heavens with the naked eye. Even a century ago, astronomers thought the Milky Way was the entire universe and had no idea that it was expanding. Today, we have telescopes that can see to the edge of the observable universe. We have theoretical frameworks that make precise quantitative predictions, and we have the technology to test those predictions against reality. This is an extraordinary time to be interested in cosmology, and the discoveries being made today will shape our understanding of the universe for generations to come. As we close this extended exploration, I want to leave you with a sense of where we stand regarding the central question. Have scientists proved we are living inside a black hole? No. The evidence is intriguing but not conclusive. The theory is creative and addresses some problems in cosmology but remains speculative. More observations are needed, more analysis, more testing of predictions. The galaxy rotation asymmetry observed by James Webb might turn out to be the first solid hint of a cosmic rotation inherited from a parent black hole, or it might be explained by more prosaic factors. Time and further research will tell. What we can say is that this is an active area of research, that reputable scientists are taking it seriously enough to publish papers and analyze data, and that the coming years will likely bring new observations that either strengthen or weaken the case for black hole cosmology. In the meantime, we can appreciate the boldness of the idea itself, the willingness of researchers like Nikodem Poplawski to develop and promote theories that challenge conventional wisdom. Science needs iconoclasts and creative thinkers who are willing to explore possibilities that others dismiss. Not all such explorations lead to breakthroughs, but the ones that do often revolutionize our understanding. Whether black hole cosmology will prove to be one of those revolutionary ideas or will fade into the footnotes of cosmological history remains to be seen. But the attempt to test it rigorously, to gather evidence and make predictions and compare those predictions to observations, is valuable regardless of the outcome. This is how science progresses, through the interplay of bold hypotheses and careful empirical testing, and we are privileged to observe this process in action. Thank you for joining me on this deep dive into one of the most speculative and fascinating ideas in modern cosmology. If you enjoyed this exploration and want to see more content that tackles big questions with rigor and nuance, please consider liking this video and subscribing to the channel. Your support makes it possible for me to continue creating these in-depth examinations of the cosmos and our place within it. Until next time, keep looking up, keep asking questions, and remember that the universe is far more amazing and mysterious than we can fully comprehend. Sleep well, and dream of infinite universes nested inside black holes stretching back through eternity, or of a single expanding cosmos born from a singular beginning, or of whatever model of reality speaks to your sense of wonder. The truth is out there, waiting to be discovered through patient observation and careful thought, and perhaps we will live to see it revealed.